Hello, this is Dr. Gardner. We're going to be looking at how to draw some more advanced Lewis structures in this tutorial. So I've expected you've watched my previous tutorial. The skills you need in order to understand some of the topics we'll be discussing here will include how to count your number of valence electrons for your different atoms in a molecule or ion, and then you need to know how to draw some basic Lewis structures, so the techniques that we used before in the past to count valence electrons, draw our Lewis structures of molecules or ions. I expect that you have mastered all of those topics and that we can now continue on to looking at some more advanced considerations with Lewis structures. What you can do if you're still learning how to draw Lewis structures, if you'd like to, you can practice drawing the Lewis structures for each of the compounds in this tutorial and then go back and look at the more advanced considerations that we will be focusing on. So first of all, what we want to look at here is how to draw resonance forms for our Lewis structures. We'll find out that resonance forms are a variety of Lewis structures that help us describe a single molecule or ion that we may be interested in. We will also then begin looking at what a hybrid of these structures are with respect to describing the actual species. And then we'll consider when we may have complex ions called Zwitterions and how that relates to resonance structures. And at the very end of this tutorial today, we'll be looking at resonance structures when we have what are called carbocations. Now, carbocations are very important when understanding organic chemistry, so I expect that you would want to watch the Zwitterion discussion and the carbocation discussion if you're continuing on to organic chemistry or biochemistry in your future. If you do not plan to continue on to those types of courses, the most important portions of this tutorial will be looking at the resonance forms and the resonance hybrid structures first to master those skills. Now, first of all, if we're going to draw resonance structures, we are going to draw a Lewis structure for a molecular ion, and if we find that there's more than one stable Lewis structure that we can draw, then they may potentially, all of the stable Lewis structures we can draw might explain the stability of these types of molecules and what's happening with them in greater detail. So to draw my resonance structures, all these equally stable Lewis structures we might have, there's a few rules we must follow. First of all, the resonance structures must have the same number of valence electrons. So we must have the same number of electrons in every one of our resonance structures we draw. We're not allowed to lose any or gain any extra. However, we are allowed to move the electrons around in our Lewis structures as long as we leave the atoms in one place. So the second rule we're going to follow here is that the octet rule must usually be obeyed. What I mean is that there's certain circumstances where if we expect we have 8 electrons around some of the elements on the periodic table, that rule will normally be obeyed. Now that I've said that, I did say usually. So let's consider some cases where we're not following the octet rule. First of all, hydrogen may never have more than 2 valence electrons, but it does not need more than that. So 2 valence electrons should be located in hydrogen in your Lewis structures. Now, if we look at the second period elements, lithium on over to fluorine, we expect that they will never have more than 8 valence electrons. This is very true. We expect they're going to follow the octet rule in all cases unless they're forming more complex types of ions. Okay, so the one case where we might see an exception of that today is when we consider carbocations. When we have a carbocation, we will often have a carbon atom with too few electrons, so it will have an incomplete octet, and it will have a positive charge for that carbocation. In that circumstance, we're breaking the octet rule, but that tends to be a species that is reactive and may not be present long term. Now, the third rule here to realize is that the period 3 elements and beyond have access to higher energy orbitals and a larger number of orbitals than we were seeing with the period 2 elements. So we have d orbitals, for example, close in energy that can be evolved in bonding. Now the third period and beyond with respect to the elements that we look at sometimes have what are called expanded octets. Sometimes they will break the octet rule by having more extra electrons present around, especially a central atom. So we might see 10 or 12 electrons in these expanded octet examples. The most common types of elements we might run into in our Lewis structures with expanded octets might be chlorine, bromine, iodine, phosphorus, or sulfur. Now the third rule I've already mentioned briefly, but when I'm drawing my resonance structures, my variety of Lewis structures that are stable to describe this single molecule or ion, I'm not allowed to move any atoms around as I'm drawing these Lewis structures. I'm only allowed to move electrons. Okay, so don't change the position in space of any of the atoms that we're looking at in the structures. Now I am allowed to move electrons around, so my resonance form should show electrons that have been moved to or from lone pairs or to or from double bonds, for example. Those would be common examples. When I'm showing that electrons have been moved, or if I'm showing the different resonance forms that I have, I'll use a variety of arrows. So let's say I want to describe each of my resonance structures, each of my resonance forms that I've drawn, and basically show that they're all contributing to an overall resonance hybrid form. Now I often will show double-headed arrows to indicate each of the resonance forms as a contributor. I really have a hybrid of all of these resonance forms. That's the best description that we'll be calling that resonance hybrid. Now if I show curved arrows, that often will indicate as a bookkeeping tool electrons that have moved, electrons that have changed their position from lone pairs or multiple bonds in the Lewis structures I've drawn. That will help me depict when I have an electron pair moving from a bond to a lone pair or from a lone pair to a bond in my structures. Now let's practice looking at a few of these. First of all, let's consider ozone. If I look at the Lewis structure for ozone, well, the first resonance structure I can draw will have 3 bonded oxygens. And these 3 bonded oxygens will have a double bond between 2 of the oxygens, a lone pair on the central oxygen, and then we'll have 2 lone pairs on the oxygen on the left and 3 lone pairs on the oxygen on the right. What we'll see in this type of circumstance is that we can have another possible resonance structure. We could have the other possible resonance structure with the atoms in the exact same position. In fact, that was one of our rules. We're not allowed to move atoms when we draw our resonance structures, but we are allowed to move electrons. So if I show this circumstance, I still have a lone pair on the central oxygen, but the oxygen on the left has 3 lone pairs. So I've moved a lone pair there. And then I have 2 lone pairs on the oxygen on the right. So I've also moved a lone pair there. So if I show if I show a curved arrow to indicate where electrons have moved, I can indicate that a lone pair here on one oxygen moved to form a double bond, and I can indicate that one of the double bonding electron pairs moved up onto an oxygen as a lone pair. Okay, so that's indicating what's happening with the electrons as I draw my resonance structures. Now I can show a double-headed arrow to indicate my 2 resonance forms. Now both of these resonance forms contribute to what we call an overall resonance hybrid. To understand what a resonance hybrid is, let's consider an analogy. Let's say that you're trying to explain to a young child what a rhinoceros is. Okay, so if we have a rhino, and I'm trying to explain what this rhino is with respect to different mythological creatures that maybe the young child knows from reading fairy tales. Maybe the child knows what a dragon looks like. So let's say a dragon is quite bulky and strong and tough, maybe with tough skin. Okay, but it doesn't really exist, does it? So the dragon doesn't exist. Maybe the child also knows what a unicorn is with its horn. So if you're trying to describe a rhino, you might say, well, it has some properties of a dragon. If a dragon were real, it's quite strong, a bulky body. It has a horn on its head, kind of like a unicorn. Even though a dragon and a unicorn aren't real, they help describe the rhino. Okay, if you're using this analogy. Now, what we have with the rhino here is a resonance hybrid. So I'm trying to describe a resonance hybrid. So this resonance hybrid that we're looking at will have properties of both of the resonance forms. Now let's see how they really discovered resonance hybrids. When they were looking at resonance structures, they started to look at some of these bond lengths, and they were seeing if they could capture one of these resonance forms and actually study it. Now, to understand this, let's consider the knowledge we have about bond lengths. So if I consider how long bonds are, a single covalent bond between 2 oxygens, or 2 of the same types of nonmetals, would be the longest type of bond we have. A double bond actually ends up being a little bit shorter. Then if we have a triple bond, your triple bond is going to be the shortest. So if I'm looking at this, the length increases from right to left, with single bonds being the longest. Now if I were to look at one of these resonance forms, and if we were able to capture this and actually see this species, we'd expect that as we studied the bonds between the oxygens, we would potentially see a medium length bond, and we would potentially see a longer bond. But what they find actually is that the bond lengths are equal here when they look at ozone. So they're not actually different lengths. And so as we're studying these bond lengths then, when they're about equal, we might say, well, are they about the same length as a single bond or about the same length as a double bond? They really don't match either one of those. We have something in between. They're in between a single bond and a double bond in length in both positions. So that indicates there's actually a partial single bond and a partial double bond in both locations simultaneously. So if we draw a resonance hybrid structure, we could go ahead and say that we have our three oxygens bonded together, but instead of having a double bond in one location, it's as if we have that double bond characteristic shared, spread out in space over all three oxygens simultaneously. So I'm going to show a dotted line here to indicate that we have that double bond character spread out through the lone pairs as well as the two multiple bond locations all at the same time. So we really have the characteristics that are mixed between these. The resonance hybrid seems to explain the structure better because it says that we should have something between a single and a double bond in both locations simultaneously by spreading out that electron density. Now when you think about electrons acting with wave properties, that makes sense that they could be spread out through all of these orbitals simultaneously, because if we don't treat them as acting as a particle, that makes complete sense. Okay, so really we have a resonance hybrid rather than the resonance structures, but each of the resonance structures helps us describe basically the real molecule as we understand it by these fake structures. Each one of them can be a resonance contributor is what we might say. They each contribute part of the character of this resonance hybrid form. So each of the sets of resonance structures we draw today has a resonance hybrid that's between these different resonance forms. We will, however, focus on the resonance forms today. Just realize none of those are really the true big picture. We have something between all of those with the resonance hybrid. Okay, now let's consider if we look at sulfur dioxide. Now if you recall, I told you to be on the lookout when we have sulfur in case we have an expanded octet. So if I have an expanded octet, EO here, we might break the octet rule with one of our resonance structures. But to start out, let's consider resonance structures that would follow the octet rule. So you first of all might go ahead and draw your Lewis structure. You'd have sulfur double bonded to an oxygen. And then we'll have a second oxygen single bonded to that sulfur. So this looks a little bit like our structure for ozone, doesn't it? So we have a lone pair on the center sulfur. We have three lone pairs on this oxygen on the left and two lone pairs on this oxygen on the right. And so if we think about our resonance forms for ozone, well, we had the center atom with an alternating double bond, right? So we had a double bond to the oxygen on the left now and a single bond to the oxygen on the right. We had our lone pairs on the right oxygen. We had three of them, two lone pairs on the left oxygen, and we had a lone pair on the center sulfur. So there were my two resonance structures that look kind of like the ozone example. Now, however, if we consider that as we get to the third period and below, we might have expanded octets that could occur. Let's consider if we could potentially have one more Lewis structure. Now, let's consider if we expand the octet, we can form more than just a double bond and a single bond to the center sulfur. It can have more than 8 electrons around it sometimes. So let's try drawing a third resonance form where we have a double bond to both of the oxygens. Oxygens frequently will be stable in compounds when they have formed either a double bond or two single bonds, so we can start to see that there's some instability here when we have just a single bond to an oxygen. If you want to predict this better, you can learn some skills that are called calculating formal charges, which I'm not focusing on in this specific video. Now, if we show an expanded octet, we could go ahead and move a pair of these valence electrons down to the single bond to form a double bond, and we could end up having a double bond to both oxygens. Now, since we already had a lone pair on the sulfur, we can only have this occur by breaking that octet rule that I was warning you about. So I still have the lone pair on the center sulfur. So these are all resonance forms that contribute to the overall resonance hybrid of our structure. So we really have some single and double bond characteristics in all three of these types of structures simultaneously, so we have it spread out over all three atoms, the oxygen, sulfur, and the other oxygen on the right. Okay, that's simultaneously occurring. So these are all telling me a little bit about the characteristic of this molecule based on our studies. So the bonds don't actually have one that's longer and one that's shorter. We actually have it in between all of these. We have some single bond and double bond characteristics simultaneously in both positions. Okay. Remember, these two followed the octet rule. So we followed the octet rule here. The last structure that we drew had an expanded octet that we were looking at. Okay, let's consider the nitrate anion. So let's consider some resonance forms for nitrate. If I draw the resonance structures for nitrate, we're going to follow the octet rule in all these cases because we're dealing with elements in the second period. So we're going to have a central nitrogen. We're going to have 3 oxygens bound to that central oxygen, or central nitrogen. And if we draw the Lewis structures for this, we'll see that there would have to be a double bond to nitrogen to fill its octet. So we put a double bond to one of the oxygens, and I put lone pairs on each of the other oxygens that I have. Okay, and if I consider this as an anion, everybody has a full octet there in that structure, we have a negative charge. Now that's one possible resonance structure. Hopefully you can see that we could draw some other resonance structures where we could have this double bond to the oxygen on the top could be in any 3 of these positions. So we should have 3 resonance structures that you can observe. So let's draw the next resonance structure. The next resonance structure would have a single bond to the oxygen on the top. I'm not moving any atoms around. I'm only moving electrons. Then I have a double bond to the oxygen to the right. So I'm going to go ahead and move this lone pair, or sorry, this bonding pair of electrons down from this oxygen to form a double bond to that oxygen. Okay. Or really, sorry, what I really am doing is taking a lone pair from this oxygen and moving it down. Sorry, scratch that. And I'm taking a pair of electrons from this double bond and moving it up and putting it as a lone pair on this oxygen here. And then I'll have a single bond to this oxygen. So here's my second Lewis structure. I should have 2 lone pairs on that oxygen. So there's 2 of my resonance forms. The third would have a double bond in this position. So what I'm going to do to have that happen is I'll move a pair of electrons from my double bond here up to form a lone pair on that oxygen, and then we'll take one of these lone pairs and move it down to form a double bond to this oxygen. So that I'm just moving electrons as I draw these Lewis structures. So my next Lewis structure will have an oxygen to nitrogen single bond in this position, a nitrogen to oxygen single bond in this position, and I have my double bond in my last position for nitrate. So there's 3 possible resonance structures for the nitrate ion. And you notice I'm using my square brackets to indicate each one of these is an ion. I show the charge in the upper right hand corner. Now sometimes you'll see all 3 resonance structures drawn and they'll just show a single set of brackets around the whole series and the negative charge in the upper right hand corner, and that's acceptable as well. If we consider the carbonate ion, it actually forms some similar types of Lewis structures. With the carbonate ion, what we'll be seeing is that we have a center carbon, and then we have 3 oxygens bound to it. Now the carbon would have an incomplete octet that way, so I should have a double bond to one of the oxygens. So you can see where this looks similar to the nitrate ion. 3 lone pairs on each of the single bonded oxygens. In order to have enough electrons, we must have a 2- charge. I'm going to go ahead and use just one set of square brackets and indicate this charge with the overall different set of resonance forms. So I'm going to draw all my resonance forms first before I close those brackets up and indicate this as an ion. So I can go ahead and have a pair of electrons from this double bond moved up to a lone pair on that oxygen, and then I can have a lone pair moved down to form a double bond here. So I could then have a carbon double bonded to this oxygen as another one of my resonance forms. Single bonded to the oxygen on the top. I could have a single bond to the oxygen to the left. Go ahead and put all my lone pairs in to complete the octets. And a lot of students who are still learning how to draw Lewis structures might do this quite a bit more slowly, and that's fine. Let's consider our third resonance form here. Now I'm going to go ahead and move one of the bonding pairs of electrons in this double bond up to a lone pair on this oxygen. And I'm going to take one of the lone pairs of electrons on this oxygen and move it down to a double bond to form the third resonance structure. So my third resonance structure will have a double bond to this oxygen, a single bond to my oxygen to the right, and a single bond to the oxygen on top. So every oxygen has some double bond character in the resonance hybrid. Because none of these forms really exist, what we have is a mixture of their properties, all in a resonance hybrid where I have a partial double bond in all 3 positions simultaneously. The wave properties of those electrons and those double bonds, or in those lone pairs, are spread out over the whole ion. They're not isolated in a specific lone location. So all 3 of these structures are very good indicators of part of the character of the actual polyatomic oxoanion. So we have some of all 3 characters in a resonance hybrid structure. Now let's consider acetic acid. When we look at acetic acid, there's a few different ways we can write it. We can write it with the acidic hydrogen up front, or we can write it at the end of the structure. This formula shows me a little more structural information, so we can see that hydrogen's bonded to an oxygen. So this is a little bit better of a formula to predict my Lewis structure. And what I can look at is if I have acetic acid and I draw the Lewis structure out, we end up with having the first 3 hydrogens in the formula bonded to the first carbon. And I'll see that the second carbon has a double bonded oxygen and a single bonded oxygen that also has a bond to hydrogen. Now when I start looking at acetic acid, it has some unique characteristics as a weak acid. So when I take the acetic acid formula and I consider what it's doing in a water-based solution, well, a very small percentage of it will react, will ionize in the water. And when that very small percentage reacts, we're going to end up forming just a few percent of the molecule forms acetate ions, CH3, COO-, and a very small percent will form protons. Now in a water-based solution, the proton actually ends up being associated with a water molecule, and we form a hydronium ion, H3O+. But chemists will frequently abbreviate this by just showing the proton being released from the weak acid. Now this is a reversible process, so I will often show a double-headed arrow back and forth. This is the major form. In solution is the molecular form. The minor form in solution, so the minor form over here, will be the ions in solution. So only a small percentage actually produce protons. A strong acid would do this nearly 100%. But my weak acids, very little of it forms those protons. Now, what I want to show you is how our resonance set of structures can explain the stability of the acetate ion as it loses its proton. So let's go ahead and look at an acetate ion's Lewis structure and see if we can come up with some resonance structures for it. So if we look at acetate, we have the first part of my Lewis structure looking the same. The first carbon has 3 hydrogens singly covalently bonded to it. The second carbon has a double bonded oxygen, a single bonded oxygen to it. And however, since we no longer have the acidic hydrogen, we actually have just a single bond to this oxygen that I've shown. And we have a pair of lone pairs on the oxygen on the top. And we left the electron behind as we formed the proton, so we have a negative charge here in this position. Now that would be one of my resonance forms, but there's no reason why the double bond couldn't be in the alternative position and why this negative charge couldn't be located on the oxygen on the top. So I could move a pair of lone pairs down to form a double bond here, and I can move one of my bonding pairs of electrons up to a lone pair on this oxygen here. If that's the case, I can form another resonance form. So my other resonance form would have the same left-hand side of the Lewis structure. I still have carbon single bonded to 3 hydrogens, but where I had my COO negative group, now this in the acid was a carboxylic acid group, but where I have this part of the acetate ion, we actually will see that that's where we have the resonance occurring. And so we could have a single bonded oxygen here in this position. And we could have a double bonded oxygen in this position with just 2 lone pairs rather than 3 once we move those electrons. So I have a negative charge on this species, on this oxygen on the top. So we can see that we just moved electrons, we did not move atoms around. So both of these help explain what's going on with stability with why I would lose that acidic proton to a small amount of ionization in water. You notice I showed my square brackets and my charge in the upper right hand corner to indicate that these are my polyatomic ions. Now, if I look at just this part of the molecule where the carboxylic acid group had been initially, what I can do is represent a variable carbon group with an R. So let's simplify that. Let's just say we're saying that R group is CH3 in this case. Okay. That's bonded to the second carbon, and we're seeing that we have both oxygens with resonance forms involving a double bond, but we actually have a resonance hybrid where the double bond is in both locations simultaneously, or we have electron density as a lone pair. So I'm going to show a dotted line to indicate that this is spread out, and then I have 2 lone pairs that are always present on each oxygen. So the resonance hybrid has that negative charge spread out over both of the oxygens, which stabilizes it so it can lose its proton in water to act as a weak acid. So all carboxylic acid containing organic molecules with the COOH type of group can act weakly acidic because the resonance structure can stabilize by spreading out that negative charge. Okay, so it stabilizes the loss of the proton for ionization, at least enough for a few % of the acid to ionize, depending on its concentration and the temperature of the room. Okay, so this was an example of the resonance hybrid for the acetate ion. Okay, now let's consider some slightly more complex scenarios. Let's consider if we have an amino acid. And let's think about what happens when it might weakly ionize, because it also contains a carboxylic acid group. Now, when we consider this topic, we're going to start looking at what are called Zwitterions with resonance structures. So I'm going to show you some ions in just a minute. First of all, we're looking at the unionized Lewis structure here. And so if I look at this structure, we're not going to draw any resonance forms. But if I look at the amino acid called glycine, we'll see that there's a nitrogen with 2 hydrogens bonded to it and a lone pair of electrons, and that's bonded to a carbon that has 2 hydrogens. And then the second carbon is where we will notice a carboxylic acid group. So we have a double bonded oxygen, a single bonded oxygen, which is also bonded to the acidic hydrogen. So what's kind of interesting is if we look at an amino acid, well, amine groups are basic, kind of like ammonia. So if you think about what ammonia does in solution. Now ammonia is NH3. Ammonia in a water-based solution acts as a weak base. So when it reacts with water, we'll end up with a small percentage of it. So since it's a weak base, only a few % does this. So I'm going to show a double-headed arrow to indicate most of it. The major form is the ammonia form, and the minor form will pull a proton off of water to form the ammonium cation. And then we would leave hydroxide behind. So what happens when I have an amino acid? This amine group, we call it a primary amine, has nitrogen with 3 bonds to it, just like ammonia has 3 bonds to it, except there's 3 hydrogens here. Here we have 2 hydrogens and a carbon. But guess what? This lone pair of electrons on the nitrogen is still weakly basic. It can still pull a proton off of water, except in this case we form basically an R group for this carbon-containing group here, bonded to nitrogen. And then as we pull a hydrogen off, we end up with an additional hydrogen to be an NH3 group that's positively charged. The only reason it's NH3 positively charged here is because we have a bond to carbon rather than to that 4th hydrogen. So we can think that amine group is slightly basic. The carboxylic acid group on the other side of the amino acid is weakly acidic, just like we saw with acetic acid. So these are very unique molecules that have acid and base characteristics simultaneously. So very important because they will combine with forming what we call peptide bonds by the carboxylic acid group reacting with the amine group and then nets amino acid over. That's so critical in biology because that'll be involved as we start to form basically proteins, and those proteins can end up resulting in a variety of structures in the body, such as enzymes, or they can be present in different type of structures like muscle tissue in the body. So it's very important types of reactions we're looking at. Now let's consider some resonance forms as we start to form these ions. Now we don't have to pull the proton off of a water molecule. Let's say we lose the acidic proton off the carboxylic acid group, and let's provide that to the basic amine group here. Okay, so if we do that, we'll end up with an anion where the carboxylic acid group was, just like we formed the acetate ion with the acetic acid. We end up with forming a cation where the amine group was, and we end up having a very interesting molecule. It actually has an anion portion and a cation portion. So it's an ion, but it's a cation and an anion simultaneously. If I look at it, it's still a neutral species because the positive charge and the negative charge, if I add those up, it's an overall 0 charge. But we have an isolated positive on one end and an isolated negative charge on the other. So we give that a very special name when we have a unique species like this. This is going to be an ion that we call a Zwitterion. Now, Zwitter in German meant a hybrid. So we have a hybrid ion that has both a cation present and an anion present simultaneously, even though it's a neutral molecule overall still. We see this frequently happening in biology with proteins and amino acids and these types of structures. So it's very useful for understanding some of the chemistry in biology. Now, in this case, though, let's look at any resonance forms we might have. So the nitrogen now has 3 hydrogens bound to it and a carbon. And that's my positive portion of the Zwitterion. So that's my cationic portion of the Zwitterion. So I have a positive charge on this end of the molecule. On the other end of the molecule, we still have CH2 in the middle of my amino acid. And on the right-hand side, we have a carbon double bonded to oxygen and single bonded to oxygen, with my negative charge overall on the single bonded oxygen, and 2 lone pairs on this double bonded oxygen. So now that's one of my resonance structures. The other resonance structure looks very similar. In fact, it has this portion of the molecule looks identical, so I'm just going to show that as an R group. I could redraw that all if I wanted to. But where I'm getting the resonance is still where the carboxylic acid group was. So I go ahead and see that there's a single bonded oxygen in the second resonance structure and a double bonded oxygen in the second resonance structure. And then my negative charge is here, so I'm still spreading that charge out overall. Now my R group is still positively charged from where the amine group is, so it's still a Zwitterion. If you don't want to use this R group, just go ahead and draw in the NH3 and the CH2 groups off to this side, and you'll see the 2 resonance forms. But this really explains what's happening when we form an anion from a carboxylic acid group when we're in the presence of a basic group like the amine group that we have here. Okay, this also can be used to help explain what's going on as we form peptide bonds, as we form what are called dipeptides. Now, the second type of structure I want to show you involves what we call a carbocation. Now, a carbocation will be when we have a positive charged carbon that's breaking the octet rule that's adjacent to a double bond, what we would call an alkene type of bond. So when we use that term, we can say this is an allylic carbocation. All that means is we have a positively charged carbon atom in the structure that is adjacent to a double bond. That's all that terminology means. So if we go ahead and look at this carbocation here, where this allylic carbocation, we have a double bond between the first two carbons, and we have two hydrogens bonded to the carbon on the left in my Lewis structure, and then I have a single bond here to my carbon on the right, and I have two hydrogens bonded to it. And then I have the center carbon has a hydrogen bonded to it. And you see hints from the structure. This hydrogen is bonded to that carbon in the Lewis structure. These hydrogens are bonded to that carbon. And these hydrogens are bonded to that carbon. So if I look at this structure, we're breaking the octet rule with the carbon on the right. So we'd have to have a positively charged carbocation in that case. Now we can see that there could be some resonance forms for this. The second resonance form would be moving some electrons around, and we'd end up with the carbocation on the other carbon present in the structure. So we could go ahead and consider that scenario where we have carbon single bonded to the center carbon, double bonded to the carbon on the right. We have single bonds here and here. And then we have two hydrogens bonded here and a hydrogen bonded here. So I didn't move any atoms really, I just moved electrons around, even though I haven't shown the same angles everywhere. Now we have a positive charge for the carbocation on this carbon. And what really happened was we moved basically a pair of electrons from this double bond over in the carbocation carbon. As we did that, we left this carbon deficient of electrons and we made it the carbocation. Okay, so those are my two resonance forms. Now the resonance hybrid is actually between this. It shows you that carbocation can be stabilized by being present in two locations simultaneously. Similar to how we saw the carboxylic acid group, as it ionizes to lose its acidic hydrogen, we can stabilize that negative charge being spread out over two locations. We're seeing the same type of scenario here. And that can help us predict reactions in organic chemistry when we start to try to decide what we call the mechanism of forming a new molecular compound. Okay, now I'd like to show you benzene's resonance structure. Now I need to give you a few hints about what benzene is. Benzene C6H6. It's actually a very interesting structure that's a six-membered cyclic ring. So I have the 6 carbons in a cyclic ring, so let's go ahead and draw that. So I have 1, 2, 3, 4, 5, 6, and kind of a hexagon shape here. 1, 2, 3, 4, 5, 6 single bonds, and then there are 6 hydrogens bonded to each of the carbons. Now we see the carbons have an incomplete octet, so I'm going to have some double bonds. So I have a double bond here, here, and here to complete the octet for each of the carbons. Now I can have a second resonance structure without moving any atoms around. So I still have my 6 carbons in their cyclic structure, and I still have my 6 hydrogens bonded to each of those carbons. And so what I can see then is I can move my double bonding electrons from one pair of electrons from my double bond over to where I had a single bond, and I can do this all the way around the whole ring. So I ended up with a set of double bonds in the alternative positions. So there's my resonance structure. I just moved those. Now I still have my hydrogens present. They didn't move. Their bonding didn't change here. So now I have 2 resonance structures to explain benzene. Now benzene is a very flat, planar molecule. It's a carcinogenic molecule, so it's known to increased risk for cancer. When I say carcinogenic, cancer causing. Okay, it's a very stable molecule though, so it doesn't decompose readily because of this alternating set of double bonds in the two positions. It's spreading that characteristic out. Now, a lot of times we can go ahead and show these types of benzene structures, and I can simplify this. We can often show the bonds between the carbons just by showing a hexagon with the double bonds, and then the hydrogens aren't shown sometimes as a shorthand notation. So this is a line bond structure. If we show the other resonance form, we could see the double bonds in alternating positions. So those would be my two resonance structures if I'm using my shorthand notation. Now I know I have a resonance hybrid where those double bonds are spread out in all locations simultaneously. So sometimes to indicate this, we'll see benzene drawn with its shorthand notation for the resonance hybrid with a circle in the center. To indicate that double bond characteristic is spread out through what we call pi orbitals in p orbitals across all of the carbons simultaneously. Okay, so that's something you might see. Now sometimes we'll look at a toluene molecule. A toluene molecule has a CH3 group up here, but really it has the same type of resonance structure. It just has 3 hydrogens bonded to a carbon off of it. So if we consider that, since it's similar to toluene, let's think about when we have a carbocation present where toluene would have its CH3 group. So I have the benzene type of structure. I have a carbon off of the benzene structure with a CH2 group on it. Now if we consider this type of structure, and I'm going to use my shorthand notation to indicate this, I'm just going to show the lines between the carbons. Here. I have CH2 plus up here. So there's my carbocation. Now I know I can have another resonance form where I could have the double bonds and the benzene ring in a different position. So I could go ahead and look at my shorthand notation where I'm just indicating all my bonds between carbons. I'm not showing the individual hydrogens here. If that's the case, I can have the electrons move to this position, and this position. So I just have them all alternate around the ring, right? And I still have my carbocation off of the ring. Now what's interesting is when you have this carbocation present, you can have quite a few more quite a few more resonance structures by moving some electrons on one of these double bonds to bond to that carbocation. In fact, this is going to stabilize the carbocation. We now can have a structure where there's a double bond to carbon. So there's some double bond characteristic to this carbocation. Sorry, there were 2 hydrogens there. So the CH2. And what happened is I moved the electrons up. That positive charge is no longer present here. We left this carbon deficient. So my carbocation location is alternating positions with my resonance structures. Now that can go ahead in resonance form move around the ring. So we can go ahead and move this double bond up to this position. So we go ahead and have another resonance structure with this carbocation present. Whoops, let me start over on that one. So if we redraw that, we're going to move this electron pair up to this position. We left this one in this position. Now we have a carbocation here, and we still have the double bonded carbon on the top of the ring structure. So there's my 4th resonance structure, and then I'm going to draw a 5th. So here's my 5th resonance structure that we can draw. So we go ahead and draw a 5th resonance structure, and with that 5th resonance structure, we're going to move this double bonded set of electrons down here. So I moved it to this, between these 2 carbons, and I have my carbocation in this position. So we can see we can draw quite a few different resonance structures to indicate the stability of the carbocation as that positive charge can be spread out over all of these different carbons in my resonance forms. We actually have something between this where this positive character of the carbocation is in all positions simultaneously, but it really explains why there's stability there. Okay, so I want to look at just one last resonance structure with the phosphate ion. Now, if I'm looking at the phosphate ion, we're going to consider a case where it's following the octet rule, but then we'll consider, well, what would happen if it starts breaking the octet rule? So first of all, if we have phosphorus bonded to 4 oxygens, we'd have to have just single bonds to all of the oxygens in the resonance structure. Okay, if we were to do that, have this type of species present. But let's break the octet rule and let's bring a pair of electrons down to form a double bond. So I could have phosphorus with one of its resonance structures with a double bond. Let me move the phosphorus over. Let's look over here. So there's phosphorus. I'm going to put a double bond here to this oxygen on the right and single bonds to the other 3 positions. So we broke the octet rule here. We have 3 lone pairs on each of these 3 oxygens. And 2 lone pairs on this oxygen. So there's one possible resonance structure where I moved electrons if phosphorus can break the octet rule. Now I need to think, can phosphorus do this? In the 3rd period and below, we can have some of our atoms breaking the octet rule, forming expanded octets. So that's definitely possible. Now I can have my resonance structures with the double bond alternating between all 4 oxygens. So I can have a structure where I have the double bond to the upper oxygen. Now I'm not going to show all the lone pairs, but you can go ahead and draw those in there. I'm going to have 3 lone pairs on any oxygen that has a single bond and 2 on the oxygen with a double bond. I just haven't shown them here for brevity. Then I could have a 4th resonance structure with phosphorus double bonded to the oxygen on the left and single bonded to the other 4 oxygens. But I can also have another resonance structure. As I said, I want you to go ahead and put the lone pairs in. I haven't drawn them in. We can have a last structure where we have a double bond down here to the oxygen on the bottom. So I can have that lone pair, a pair of electrons from this double bond move up to a lone pair on this oxygen, and from a lone pair on this oxygen down to a double bond to form that. So I end up with a double bond to this oxygen and a single bond to the other 3 oxygens. So we can see the phosphate ion. In fact, if I want to indicate this is a phosphate ion, I can go ahead and put square brackets around all of my different resonance structures with their positive charge. Sorry, they're not a positive charge in this case, a 3- charge for phosphate. And I can show that charge for the oxoanion here over all of those different resonance structures. And these resonance structures are quite important for understanding the chemistry of phosphate in biology. So that's why I wanted to show it to you. Okay, so make sure you practice drawing Lewis structures with resonance forms. Think about what a resonance hybrid is with respect to the actual species you have present. Okay, thank you very much. Take care.